Have you ever looked inside a watch or a car transmission and felt completely overwhelmed? Those spinning metal teeth look incredibly complicated, but really they are just speaking a simple mechanical language, one that lets us easily control speed and power. To understand that language, we need to forget about the circles and the complex machinery for a minute. We are going to start with something much simpler, a straight stick. This is a basic lever, a straight line resting on a center triangle, called the pivot. Notice how a tiny block sitting way out on the far left edge easily lifts a massive block sitting right next to the pivot on the right. That happens because of a strict mechanical rule. When you increase your distance from that center pivot point, you directly multiply your pushing force. You trade physical distance for mechanical strength. A lever is a fantastic tool for multiplying your physical effort, but it has one obvious flaw. Push down far enough and your stick hits the ground. The movement stops and your mechanical advantage is over. How do we fix that? How do we build a lever that never hits the dirt, allowing us to keep pushing with that multiplied strength continuously? Cross multiple levers over a center pivot and you always have a fresh stick to push. Fill the gaps to form a solid circle and carve notches to grab things. That's a gear. Because it spins, engineers call this force torque, the gear's twisting muscle. That twisting muscle is very different from speed. Speed is purely a measure of how fast the circle itself completes a rotation around its center, regardless of how much muscle it has behind it. By turning a strict stick into a toothed wheel, we created an infinite rotating lever. This brilliant design lets us continuously apply multiplied physical force without ever having to stop and reset our machinery. A single spinning circle is useful, but the real work happens when we lock two of them together, especially if they are different sizes. When we do this, we run into an unbreakable rule of physics. We can choose to multiply our speed, or we can choose to multiply our torque. We can never get both at the same time. Let's look at an animation showing how we gear for power. Here we have a small driving gear with exactly 10 teeth, turning a larger gear that has exactly 20 teeth. Because the teeth have to lock together perfectly one by one, the small gear has to spin a complete 360 degrees just to push the large gear halfway. It takes 2 full rotations of the small gear to force the big one through a single rotation. We sacrificed speed. The big gear is moving much slower than the small one. But in exchange, the larger gear now has double the twisting muscle. It can push twice as much weight. We can also flip the arrangement if we need a different outcome. If we attach our power source to the large 20-tooth gear, we are gearing for speed. As the animation demonstrates, pushing that big gear through just one slow turn sweeps 20 teeth past the connection point. That forces the small gear to spin twice. We gave up torque, but we doubled our speed. This becomes incredibly useful when we line up more than 2 circles. When we chain multiple gears sequentially like this, we create what engineers call a gear train. By stringing enough of them together, we can take the weak, high-speed blur of a standard electric motor and steadily trade that speed for power, gear after gear. At the end of the line, the final wheel moves at an agonizing crawl, but it packs enough torque to lift a massive drawbridge. This makes gear trains the ultimate mechanical problem solvers. They let engineers take whatever energy source they happen to have and convert it perfectly to match the exact mechanical task they need to perform. You don't have to look at engineering diagrams to see this exact trade-off happening. You already feel it in your daily life. When you pedal a bicycle up a steep hill and your legs start burning, you shift into an easier gear. You are actively moving the chain to a larger cog on the back wheel, sacrificing speed so you can multiply the torque of your legs to overcome the climb. Or when you are driving down a flat highway at 60 miles an hour, your car transmission shifts into overdrive. It uses a large gear to turn a small gear, sacrificing unnecessary pushing power so the wheels can spin fast while the engine relaxes. Every complex transmission, every mechanical clock, every motor in your house is relying on the exact same trick. We are just using spinning levers to negotiate with the laws of physics. Once you see a gear for what it really is, a simple stick balanced on a pivot, wrapped into a continuous circle, the machines around you stop looking so intimidating. They are just problems that have been solved, one spinning lever at a time.